we now move to the class weights. Now if we look carefully at this output right here, you'll notice that first of all we have three classes, that is the background, the boundary, and the object itself. But the problem we have here is that some of the classes are out of these three classes, they are not all represented in the same way. So it's not like a situation where we have the background pixels being equals the boundary pixels, and which is also equal the object pixels. So in this case where we have these three different classes which all have different or have in general different number of pixels to occupy, we'll see that what the model will be learning, or better still the way our model is going to be learning to come out with this segmented outputs, will be such that it tries to favor the most represented class, which in this case is the background class. So we shall most likely be having outputs which have the backgrounds correctly classified, whereas the boundaries and the object aren't well classified. And this is because, as we've said, the background is most represented, followed by the object, and then the boundary. And so to modify this, we have to modify our loss function such that we give weights to each of these classes. For example, the background could have a weight such that the loss we incur whenever we misclassify a boundary should be 4 times that of the loss whenever we misclassify a background. And this will play the role of punishing the model even more severely whenever it misclassifies a boundary as compared to whenever it misclassifies a background, simply because we have more background data as compared to the boundary data. Also, we could have a ratio of the weights for the background and the object. So from this we could pick out, say, a ratio of 1:2:3, where the boundaries affect our output loss the most. So to do that, we could now recreate our loss function by creating the custom loss right here. So there we go. We have this custom loss which we've just redefined. Now note that there is no major difference between this custom loss and the loss we've been working with so far. So let's take this. We have now the custom loss. And so if we, for example, fix these factors to say values of 1, 1, 1, then this is exactly the same as this custom loss. Now let's understand exactly what's going on with this custom loss. We first start by having this categorical cross entropy loss defined, and then we have the y truths and the y preds, which are broken up into 3 parts. There's the first part, the second part, and the third part. So unlike before where they were just put in one and then pass into this, now we have to break them up so that the loss computed from this background and this all have a weighted part to play in the total loss right here. As you can see here, we have the loss from the background, the loss from the boundary, and the loss from the object. So we have the factor background, factor boundary, factor object. When we have 1, 1, 1, it simply means we just adding this up naively, considering that they all have the similar representations. Now that we don't have that as the case, we have to actually segment this into these 3 parts. We look at this background, for example, we see we gather based on the target values wherever we have a 1. Now in the slides we had said that the background took values of 2, and that the boundary was value 1, and that the object was value 0. But actually there's a slight error with that, because the backgrounds have value 1 and the boundaries value 2 instead. So that's it. That's exactly what we get from our data set. So that's why you see we select this. So we get to the y true, which is of dimension 112 by 112 by 1. And now we pick this last dimension right here, and then we say if it's equals 1, we gather all those values. So basically what we're doing is we're gathering all the background values, or all the values where the targets are backgrounds, and then we compare it with the predicted right here. So as we could see here, we have the y true background and then the y predicted background, which are both compared, and then the loss is calculated. Then we move to the boundary. Yeah, we specify a 2 for the y pred, specify a 2, so we get these values. And then we move to the object, we specify 0 and this. Now what we could also do is we could print out the shapes of all these arrays right here. We could print out the shape, this, and this. And then if you add this plus this plus this, you'll see that it's going to give you exactly the same as 112 times 112, proving to us clearly that this is actually a value of 12,554. And this will prove to us clearly that all those values are extracted from the pixels without any error. And you will also see that this, which is the background, will have the highest number of values. Since they all have different values, this will have the highest, this will have the second highest, and then this will have the least number of values in general, actually. Since there may be some cases where the objects maybe, or the space occupied by the object in the image may be larger than that of the background, but in general the background space occupies or is greater than that of the object. So that said, let's get back to this. We could pick a factor of say 2 and then 3. So that's it. Work with floats. After training for several epochs, we see we have this loss, accuracy 97%. We could parse right here. Then doing the testing, there we go. This is what we have instead of this output right here. We'll notice that due to the class imbalance, our model is struggling to correctly classify the boundaries. So we get back to this loss. We now have the custom loss instead of the sparse categorical cross entropy loss. So we get this. And now checking back at this, we see that we made this error. Normally this should come. So we should have this right here. Okay, so we have 1, 2, 3. That's fine. So run this now. Custom loss not defined. Check on this. Okay, so there we go. We see already that the loss value leads from the 0.08 we had now to 0.8, and this is normal because much priority now is given to the boundaries. After training again for a while, we have the results. We see that the loss values are high as compared to the previous loss values while comparing the accuracies. So last time when we had an accuracy of 97%, we already had we had loss values less than 0.1 right here, and this is normal since we're multiplying our loss values by these factors. So we pause this and then we go into testing, and there we go. We see that this output now is better than the previous one, as we have this boundary contours which are well formed, although they happen to be quite thick as compared to the true values. So that said, we could also slightly modify this factor here by simply reducing it. Nonetheless, when we train on the full data set, you could better modify these factors. So we move to the next part, which is that of the reduced network. Now, instead of working with the ResNet as we've been doing throughout the section, we could now have instead a mobile net. So We have our mobile net version 2. So let's take that, run this. We have this error right here, and this is normal since we don't have this exact layer names in the mobile net version 2. So what we shall do is we'll first return the base model and then get all those values or all those layer names. So let's have that. We observe this now. Start from this, we go up to the point where we have 112, which is this block 1 expand relu right here. So instead of having this here, we take this off and we have that. The next one is 56. So we come down here, we have this block 3 expand relu. We copy this, paste out right here. Next is 28. Take this from here, paste out here. 14. Take this 14. It's taking a while. Okay, so we have this 14 right here. This should be this one, and then the last one, which is this. Okay, so we have now this right here. Then we could uncomment this. Now we also know that these names have to be replicated right here, so let's copy this, and that's fine. So if that's okay, we now recopy this again, and then we put it out here. Okay, so we're ready. So we run this, works just fine. We've left from 23 million parameter model to this approximately 2,200,000 parameter model. We have the upsample layer. See, we've taken off. Now this is okay, but yeah, we need to take this off. Could take this off. We run this, conf layer. Then we have this as usual. Run it again. We have this error. Let's get back to this here. Okay, we note that this returned this. We didn't take that off. We'll run it again. Run this, and then this. So we have this new error now in the conf layer. Object has no attribute num2. Let's get back to the conf layers. Take this off. Run it again. Now it's fine. We see that we have total of 5 million parameters where 3 million are trainable. We now go ahead to the loss. Let's take this to a value of, say, let's maintain it at 3.0. Run that. We compile, and then we run this. So there we go. Training is moving quite well. We have our loss and accuracy values which are reducing, but also note that what we could do here to avoid having this large loss values is to normalize these factors right here. So instead of having 1, we have 1 divided by the sum of all the factors. So we have here 1, 2, 3, that gives us 6. So we have 1 divided by 6. We have 2 divided by 6, and then 3 divided by 6. So that's it. Let's pause this and then test our model on the smaller network. We see that the smaller network performs quite well and even better than the previous, which tend to overfit on the data. So that's it. We could come back to this, run it again, and then looking now at the loss, we see that we have these values now, which is more representative of the loss we are having in the case where we would have been using this sparse categorical cross entropy loss. So let's take this back, and our model continues training. Let's pause this right here. Test this again. Okay, now let's look at some other doc images. You see, this is quite cool. We could look at, now this is drawn from the data set. Let's take this out of the data set. This one is not from the data set. This image isn't from the data set, so this isn't bad. We could do better than this by simply training now on the full data set so that we don't overfit on the few images we've already trained on.